So they start off with something from our last chapter. They say, can you solve negative 2x squared minus 6x plus 20? Well, I could divide everything by negative 2, and then I get a quadratic equation. I could say, should I factor, or should I use completing the square, or should I use the quadratic formula? Personally, I would try factoring first, and this one does factor really nicely. So then you know that x equals negative 5 and x equals 2 are the x-intercepts. We have our x-intercepts at negative 5 and 2. Now, on the graph, we can always find an x-intercept by plugging in 0 for y, and because we plug in zeros for y, the zeros are called zeros of the function. So another word for x-intercepts are called zeros. And you're going to find that with quadratic functions, sometimes questions are going to talk about x-intercepts. Sometimes they're going to talk about zeros. Sometimes they're going to talk about find the solutions. And sometimes they're going to talk about roots. These are all the same thing. They are all basically plugging in 0 for y and solving. Okay? Now, with the x-intercepts and zeros, usually you start with y, so you actually have to plug in 0 for y. With solutions and roots, usually it's been done for you, right? Because in example 1 there, it said solve. They already plugged in the 0 for y for you. Then those are called roots or solutions. So just wanted to write down all of those words to know that all of those words basically mean the same thing. And we already saw this nice pattern, so if you want to take out your highlighter and highlight the over 1 up 1, over 1 up 3, over 1 up 5, over 1 up 7 pattern. That's on page 254. So with that, the question is, in question number 2, if you had a table, could you tell whether or not these are quadratic functions or not? And we're going to use that pattern of +1, +3, +5, +7 to check. If I check table A, what's happening between this one and this one? I'm subtracting 3.5, right? And then what happens between this one and this one? I subtract 3.5 again. And then I subtract 3.5 again and subtract 3.5 again. Does that follow the 1, 3, 5, 7 pattern? No. In fact, when it's always the same, that's like a slope of a line. Rise over run is always the same. That makes a straight line. And the second one, here we're going up 8.5. Oh my goodness, this is boring. Is this going up 8.5, up 8.5, up 8.5? Does it make a line? I mean, it also makes a line. Does it make a parabola? No. What would make a parabola? Should we make a third table that actually, should I make one that actually works? Yeah. Let's go 0, 1, 2, 3. I'll make it a little bit tricky. Should I make just a little bit tricky? 0, 1, 2, 3. We're going to go a little bit tricky. Do you see that it goes up 3, up 9, and then up 15? How How is that a little bit tricky? What did I do to the 1, 3, 5?
You just skipped every second or
Okay, but yeah, I skipped some. Can you see that if I took these and multiplied them by 3, that would give me 3, 9, 15, 21. So this would be some sort of 3x squared graph. I don't know which one, but I know that it will have a 3x squared in it. So anytime your numbers are jumping up as a multiple of 1, 3, 5, and 7, it makes a parabola. And what always happens with a parabola is if you check the next time, the next differences, here I'll do it in blue. What's the difference between 3 and 9? What's the difference between 9 and 56? As long as it's constant after the second time, you know it makes a parabola. That'll always happen. If it's the same after one time, it makes a line. You're going to find out later that if it's the same after 3 times, it would make an x cubed. Okay, question, just circle number 6.